Okay, so welcome everybody. This is the 43rd Flow seminar. And for those of you who are joining for the first time, Flow stands for Federated Learning One Word Seminar that provides a global online forum for the dissemination of the latest scientific research results in all aspects of federated learning. This includes distributed optimization, learning algorithms, privacy, cryptography, personalization, communication compression, systems, hardware, and many more. So today it's my great pleasure to host Hongyi Wang, who recently defended his PhD at Computer Science Department of University of Wisconsin-Madison, advised by Professor Dimitris Papalopoulos. And his work focuses on scalability and robustness of distributed machine learning applications, for instance, for federated learning. And today he's going to tell us about the efficiency and robustness of federated learning. So this talk going to be recorded and later we will make it available at our YouTube channel. Hongyi also agreed to take questions throughout his talk, so you can either just raise your hand or post your question to the chat and we will try to unmute you, and so you can have a bit of an interaction with speaker. And yeah, so I guess that's it. And Hongyi, please, the floor is yours.
Yeah, thanks a lot, Samuel, for the great introduction. And yeah, it's my great pleasure to be here to share our recent research result on the efficiency and robustness of federated learning. Okay, let's dive right in. Yeah, by the way, as Samuel just mentioned, if you have any questions or any comments or any thoughts on the slides during my talk, just feel free to chime in. Yeah, and I will discuss. I will stop and we can discuss on the fly. All right, cool. Then let's dive right in. So this is joint work with an amazing group of researchers at the University of Wisconsin and Madison, and also with our collaborators at IBM Research and the University of Michigan. So as we all know, federated learning is a promising scheme to conduct a decentralized distributed training while keeping the data privacy on the local devices. So basically, we do not let the data to left the participating devices, but we still conduct a way to jointly train the global model. So, but there are several issues in federated learning. So today I will mostly focusing on the efficiency and the robustness issues in federated learning. So for efficiency issue, there are two basically aspects. So the first is that since most of the time in several, which is called a cross-device federated learning scenario, so the participating devices can be just the mobile devices. So bandwidth can be limited there. So whenever we are curving the communication between the participating devices and the data center, so the bandwidth can be limited and the communication costs can be non-trivial. Another issue is basically the data in each of the local devices are collected in an independent way. So they may not follow the IID fashion in what we usually encounter in centralized distributed training or just conduct the training on single device. So that's mostly known as the efficiency issues in federated learning. So for the robustness issue, mostly just mentioned by recently proposed the great reviewing paper by Google last year. So it said federated learning system can be vulnerable for different type of adversarial attack. So in that sense, the federated learning system and algorithms can be lack of robustness, and so that's usually known as basically vulnerability to the training time attacks. So today I will basically discuss the two aspects by introducing you the efficient federated learning, and I will basically introduce our work in the federated matched averaging, also known as the FedMA, and also I will dive right into the robustness part of federated learning, and I will tell you the vulnerability of federated learning to a certain type of attack, which is known as backdoor attack. So let's start from discussing the efficiency of federated learning. So even before I dive right in to the efficiency part, let me quickly walk you through one of the standard algorithm in federated learning, which is known as the federated averaging. So the way it works is that at the beginning of each federated learning round, the participating user can download the current version of the model. And then a subgroup of the participating user will be sampled by the data center to conduct a procedure called local training. So basically, each of the sampled user can train the global model based on their local data. So once they finish the local training procedure, so basically ship the locally trained model back to the data center. And the data center will basically conduct averaging, which is basically coordinate-wise weighted averaging. So the weight is based on how many data points are there for each sampled clients. So in such a sense, as we discussed, the cost of low efficiency come from two aspects. One is that in this case, the participating user are usually mobile devices. So bandwidth can be limited. So whenever we encounter communication, so the communication cost can be high. Another issue is that we may need to run this algorithm for a lot of federated learning runs to make sure the global model converge well. Since the data are heterogeneous in this sense, do we need extra run for the global model to converge compared to what we run like local SGD in the centralized setting? There are a lot of to tackle this issue. There are a lot of previous work tackle the first aspect. So basically, they're trying to compress the model updates instead of shipping back the original model update to the global model. But in this work, we ask ourselves, can we improve the efficiency of federated learning with a better model aggregation rule? In that sense, we may allow to just conduct federated learning for fewer rounds of federated learning rounds, but the global models still converge well. So you may ask in this sense, isn't coordinate-wise averaging already good enough? So the answer is mostly yes, but there are still several circumstances that we need to handle that the coordinate-wise averaging may not be quite good at. So let me quickly walk you through one example. So here, assuming we have two local devices, and each of them just trained one like model, which is basically a fully connected network with one hidden layer. And each of the hidden layer just contain two neurons. So in this sense, due to the permutation invariance property of the hidden layer of a neural network, basically meaning if we permute the order of the hidden neuron in the hidden layer, so output won't change. So even if those locally trained model on those two devices have the same accuracy, so when we are trying to average them, we may still encounter an issue because those two identical accuracy model on those devices may just different in the sense that the order of the hidden neurons are shuffled. So when we directly conduct coordinate-wise averaging across the devices, we may just average the neuron that are trying to extract the different features if we think the hidden neuron as a feature extractor. So say a particular example here is that if we're trying to classify cats, so purple neuron here might trying to extract the ear of the cat, and the green neuron are trying to extract the nose of the cat. And when we conduct the coordinate-wise averaging, we may suffer the issue that we just break the feature map. So here, one easy way to basically fix this problem is that we align the neuron first, and then we conduct the averaging. That's what we called federated matched averaging. So a simple question here that basically raised here is that, so what if different clients decide to train the local model with slightly different hidden neurons, number of hidden neurons? So basically, each of the hidden layer can have different sizes. So here, client 1 basically have 3 hidden neurons, and the client 2 has 4 hidden neurons, and client 3 have 2 hidden neurons. And what if there's one hidden neuron, say the second one of the client 2 is trying to extract the features that are different from all other neurons? So in this sense, we may still want to handle this. We may still want to like our framework to handle this segments. So the way we want to do in our framework is that we're trying to align the neuron that are trying to extract the same feature and treat the neuron that are trying to extract the different features from all other neurons as an independent neuron. with that, we basically allow the basically the global layer to grow a little bit. So how do we achieve that? So we can easily formulate the problem actually as a linear assignment problem. So basically, we look at how the neurons are different from each other. So, but by directly formulate this problem as a linear assignment problem, we can find the issue here. So in this particular example, the orange neuron will be matched together for sure because those are two identical neurons. But in this particular example, the purple neuron will basically be matched with the green neuron since it basically has nowhere to go. So to allow our framework to basically the global neuron to grow a little bit more, so we basically relax the formulation a little bit by introducing an extra epsilon here. So if the epsilon is not larger than the C12 here, so basically the purple neuron will go to as an independent neuron. So we also do not want to our global model to grow larger and larger. So we for each time we add basically an independent neuron here in the formulation, we basically constrain the size basically by increasing the threshold value such that our global model won't grow too large. So to complete this formulation, so we still need to specify the similarity, the threshold, and model basically penalty function. So we can do that empirically, but one of the previous work by my mentor at IBM basically proposed the PFNM framework by basically arriving at a special case using Bayesian non-parametric approach. So basically just adopt the same approach in our formulation. So one problem there is a PFNM. It's just that they can only handle the fully connected layer. So we basically want to extend that to basically more modern neural network architectures. So let me quickly walk you through one example to handle convolution layer. So basically, in convolution layer, the hidden neuron can be viewed as the convolutional filter there. So what we can do here is just instead of matching the hidden neuron, we can just match the convolutional filters and also the biases after each of the convolutional filter. But this only handles the single layer. So how can we handle the entire neural network? So we basically have a greedy approach to handle that. So say in this particular example, we have two convolutional layers and two clients. So what we do here is just we look at the filter dimension in the convolution layer 1, and then we basically conduct the matching approach just as I described previously. Then basically the order of the neuron can be different after the matching, and the global matched layer can grow a little bit. Then based on the matching result, we basically will need to permute the input color channel because the input color channel may just grow a little bit and the order may change. So we need to permute the input color channel dimension in each of the convolutional filter in the next layer. And then we basically match the filters in the next layer after the permutation. And we basically conduct this procedure across each layer of the neural network. And finally, we arrive at matched model on the data center side. So we basically test this greedy approach after one round of federated learning. So what we basically observe is that, so on a slightly shallower model, say LeNet on MNIST, basically compared to federated averaging, we arrive at much better accuracy after one round of local federated learning round on the data center side. But on a slightly deeper model, this approach is not working quite well. So say on VGG9, trained on CFR10, so the accuracy is actually quite comparable to federated averaging after one round. So what happens there is that maybe just for the greedy approach, after we matching each layer, we basically lose some amount of accuracy. And when the neural network architecture becomes deeper and deeper, so the method is not working quite well. So to fix that issue, we basically change the greedy approach to a layer-wise matching problem. So instead of matching the neural network together at once, so we basically handle the layers, basically the network layer by layer. So the way it works is that if we still consider the example, we have two local training devices. So our framework, we basically match the first layer of each of the local model. And then basically we arrive at the global layer 1. And then after that, the data center will broadcast the matched global layer 1 back to each of the participating devices. Then what the participating devices will do is that after receiving the matched global layer, it will freeze the matched layer and basically retrain the consecutive layers based on their local data until convergence. So you may imagine this is a computationally expensive task, but I encourage you to basically check the literature of transfer learning. So we will basically freeze the previous layer and just treat the consecutive layers. So basically, we will take quite much fewer epoch for each of the local devices to converge compared to you just training from scratch. Then we basically we repeat this procedure for each of the consecutive layers. Basically, after matching the global layer 1, we basically handle each of the local layer 2, and we basically match each of the local layer. And we repeat this procedure until we arrive at a global network. So note that for the last layer, the hidden neuron is basically the number of classes. And then we will basically, what we will do is just that we will conduct a weighted averaging across the weights of each of the classes in the weighted averaging way, which is essentially similar to federated averaging. So we basically the weight is but depend on, like, for each of the class, how many data points are located on each of the local devices. So in this sense, so I want to notify you that for the federated matched averaging is that so to finish one iteration of federated matched averaging, basically the communication amount is the same as federated averaging and the FedProx, basically, which is the size of the entire model. But the number of communication rounds we need to incur is with respect to number of layers in the model. However, in federated averaging and FedProx, it's basically only require one round of communication. So by adopting this approach, we basically arrived at a much better like accuracy, even to handle a deeper architecture compared to the like a greedy approach I just described before. So so our experimental result basically showed that so here, so in the left figure, the x-axis is the amount of communication, and the y-axis is the test accuracy we achieve finally on the global model side. So with respect to the same amount of communication, so if we conduct matched averaging, we can arrive much better test accuracy compared to the federated averaging and the FedProx. And even if we count the number of rounds, so remember that to finish one iteration of matched averaging, we basically need the number of rounds, which is the same as number of layers in the architecture. So we still perform better compared to the federated averaging and the FedProx. So more interesting result here is that it's sort of like a known issue that for the federated averaging that so you cannot allow each of the local user to basically train their local model for too long. So basically that will cause the local model to be too far away from the global model for each of the federated learning rounds. So after that, if you basically still conduct federated averaging, the global model may suffer a bit if you train the local model too longer. So in this case, we sort of like observe a slightly different trend in federated matched averaging. So basically, our framework leverages quite good local model quality. So basically, if you allow the local model to train longer and longer, so basically basically after you conduct matched averaging, you will reach to better global model accuracy. So I think we have a question here. Let me try to look into that.
Yes, I'll try to unmute Konstantin. So please Constantine, ask yourself.
Yeah, thank you. So these experiments with Federated, Federated are with full participation. You mentioned there is like 16 local clients.
Yeah.
Oh,
That's
okay.
that's exactly what I will talk about in the next two slides. So yeah, so currently we assume that all clients will participate in each of the federated learning rounds. So so the issue comes from to match each of the layer, we actually assume that the same group of clients will participate in each of the federated learning round. So how to support how to support the different sample clients for different communication rounds is an open problem here. Yeah, but you're definitely correct. We assume all the clients will participate in the safe federated learning round.
Okay, thank you. Also, can you please describe one more time principles for matching? Is idea take layer by layer and create a specific rule for each type of the layer? How this matching is happening? Can you please describe one more time?
Oh, you mean the layer-wise the matching, or just as a matching framework?
Yeah. So idea is perform some kind of matching, but how matching is performed is depend on the layer, and there are specific rules for each of the layer. Is it so?
Yeah. So the rule for each of the layers is actually the same. So so you can imagine so like in this particular example, so we are using a convolution network as an example, right? So here, basically, we are matching each of the hidden neuron. So what is a hidden neuron in convolution network? Is basically the convolution filter, right? So basically, we can think of them as each of the convolution filter as the hidden neuron. So in that sense, we basically compare. So basically, look at one of the neuron here. Let's say the orange one. And we basically see how close it is, between this origin neuron in client 1 and the other neuron in client 2. So if the origin neuron in client 1 is close to the basically the third neuron in client 2, then we basically average those two instead of like just.
Okay, thank you. And how do you measure this similarity? So as I understand, we can understand like neuron is a small subgraph, and you try to estimate how these two neurons are similar.
Yeah, that's a great question. Yeah, that's a great question. So so in the current framework, we just look at so since each of the hidden neuron can be represented by like tensor or basically a vector. So in the current version, we just look at them using the L2 distance actually, which is actually arrived by this probabilistic federated neural matching work in FML 2019. I encourage you to check that work. In that specific setting, the distance is measured by the L2 distances. So, but that may not be the optimal metric we should look into. That's why I also put it as an open problem here in the end. So I think there's a great work here, like how to construct a better metric to measure the similarity between the neurons. And there's a work published in the NeurIPS 2020 that by a group of researchers at the EPFL. So basically, instead of just to do the matching, they are trying to use optimal transport to also match the neurons. So I encourage you to check that. And also,
thank you very much.
Yeah. Any other questions?
Yeah, I would have one question about this, like about the matching approach. So what, like as a server, what do you need to know? Like, is there actually like, can you like support, for instance, like secure aggregation, or what, or you have to know exactly like each weight or each neuron from the client that's communicating? So maybe like with respect to privacy, like what do you need to know?
Yeah, that's a great question. So so what we will do, the input will basically the same as federated averaging. Well, I won't say exactly the same. So the current approach is not able to support secure aggregation. So basically, you need to know the weight of each independent client. So Yeah, in secure aggregation, which basically you see in the end is the average version of the weight. But here we do need to know the weight of each of the participating client. So, but we do not leverage any extra, say, the intermediate output of the client that may violate the like privacy directly. And we do not leverage the fact that there is some holdout data set on the data center. So we basically only need to look into the weights of each of the client. Yeah, that's one thing. But I do believe if we are allowed to look at the activation value, so in the intermediate value here, we may conduct a better matching method based on the activation instead of based on the weight. So currently the approach is agnostic.
But for that, you would need to have this holdout data set, right? You would need to somehow
support
that everybody like propagates the same data set, right?
Exactly. That's why, that's a great question. That's also why I put this open problem here. So how to basically handle, how to basically support secure aggregation. So currently, this framework does not directly compatible with secure aggregation.
Thank you.
Yeah, thanks a lot for those great questions. Do we have any other questions?
There are no questions in the chat and nobody's raising hands. So for now we have
all right, cool. Yeah, awesome. Yeah, thanks a lot for the great questions and the comments. Yeah, then let's start right into the second part, which is basically the robustness of federated learning. So I know Dimitris has presented this one before in this same seminar, but I will provide you a slightly different angle of this work. So hopefully it's not too boring for you. Okay, so once again, so in federated averaging, basically we conduct this iterative procedure that we train the global model by, iteratively conduct the federated learning runs, and we like repeat that over and over again. So it's easy to imagine here that is the global model suffer from the training time attack. So because there's no central authority to inspect each of the independent model update. So especially in the case that if you want to use secure aggregation. So what you finally see on the global model is basically just the average version of the local model. So so you have no way to inspect the local updates for each of the independent client, and like especially their data. So yeah, so basically, so federated learning is basically easy to imagine it can suffer from the training time attack. So before even like delve into this issue, let me introduce you several ways to basically inserting a certain type of attack, which is known as a backdoor attack. There's one way called a black box data poisoning attack, which basically assumes we basically have the less assumption, basically the minimum assumption about the participating attacker. So which is basically the participating attacker can be just a normal user. So what it can do is basically just manipulate its local data set. And it has no control to the training, so basically local training procedure. So it has basically no ability to hack into the software to control how the data center wants the local user to train their model. So basically the only way it can do is just to try to like change the local data sets. This is called a black box data poisoning attack. And there's like a different version, slightly different version called white box PGD based attack. Is that instead of, since we assume the attacker can hack into the system and change the training algorithm. So instead of just train the local model, say using SGD or basically Adam or whatever, it basically use like projected gradient descent. And basically for each of the local training run or iteration, it basically projects the model updates into an epsilon ball. So you can easily imagine if you conduct PGD-based white box attack, so the local model won't be too different from the global model. So so the model change is actually in the epsilon ball of the last run global model. So basically that gives the attacker extra ability to hide these local model updates. So the goal here is basically how can we conduct effective backdoor, meaning that it can be like effectively inserted into the global model, and how can that persist long? So we do not, the attacker will definitely want the attack to persist long in the global model, and how to make the backdoor hard to detect. And the fundamental question we want to ask here is federated learning robust, like to this specific type of attack, which is the backdoor attack. So back into like 2018, so there's a group of amazing researchers from Cornell Tech, which basically proposed a way to backdoor federated learning. So by conducting several certain type of semantic backdoor here, and they propose that those backdoor can be easily inserted into the global model. And then basically several years later, like Google basically jumped out and say, hey, we basically test your attack on our basically simulated federated learning environment. Then we basically found several issues. The one is that your attack might be successful for several federated learning rounds, but it does not persist long. Or if we just use some like simple defense, say just basically weight normal clipping, so it basically just defend the backdoor attack quite well. So there seems to be some active debate in that in that topic, and we basically want to answer this question concretely. So is federated learning vulnerable to backdoor attack? So the answer is affirmative. That so the backdoor is actually inevitable in federated learning. So what we found is that so before even delve into the like problem and introduce the approach, so our approach is inspired by one observation. So why does the basically backdoor attack find by the Cornell users, Cornell researchers, are not persist long in the global model? So we found one potential reason. So say, assume the attacker can insert the backdoor easily into the global model. So as the global model becomes a poisoned model here, then basically in the next round, so the global model will basically be downloaded by another group of participating users. So may or may not the participating users may or may not include attackers. Which basically it's likely that attackers may not be able to participate in the next federated learning round. So in that sense, if the attacker is trying to insert a certain type of backdoor, they're trying to make the global model believe green cars are birds, but all other users actually knows the green cars are cars, and they basically see the green cars every day, and they basically can leverage their local data training procedure and with the data set with the same pattern as with a clean label to fix the backdoor inserted in the global model. So after the local training procedure and the global averaging procedure, so the next round, the global model will become a clean model again because the backdoor just erased by other honest user like from their local training procedure. So question seems to be that the backdoor pattern chosen by the attacker is too common across according to the participating populations. So the question to ask here, so what if we attack on the tail of the data distribution? So what do I even mean by that? So let's imagine we have a data distribution here. So the most commonly observed airplane, say, we basically look at the airplane quite similar to what we just can see in the CFR10 data set. It's just a pretty common part of airplane. But there's a certain type of airplane that is much more rare compared to the normal airplane we observed every day. It's basically a United Airlines airplane. But on the tail of the distribution, there's some other airplane that can be even more rare compared to United airplane. It's basically like Southwest airline airplane. So since Southwest is basically a much smaller airline company compared to United, so there's a less chance we observe the Southwest airline airplanes every day. So basically in that case, if you look at, we look back into the pipeline again. So if we try to insert the backdoor using the Southwest airline example, so since other honest user, so in the next round, even the attacker cannot participate into the game, since other users do not frequently observe the Southwest airline airplanes. So they have less chance to erase the backdoor based on their local training procedure, such that the attack can persist longer. So in our experiment, we basically arrived at a certain type of edge case backdoor. So basically on the tail distribution of the data set for certain whole bunch of different like image classification task, a sentiment analysis, and network prediction tasks. Yeah, so just if you are curious, just I encourage you to check our paper. And so we finally arrived at a quite effective like edge case backdoor attack. So before even delve into the result, I will share you some of the theoretical analysis we conducted in our paper. So I'm no theoretical analysis expert, but I'm so proud of that our like team member proved these theorems. So the first one is that so we basically build a connection between the backdoor attack and the adversary examples. So you can easily imagine that if your data is suffer from adversarial attack, meaning that if the slight perturbation on your data points, we basically change the prediction of the outcome of your model. There's a similar way you can do is that you can also construct the adversary example by perturbing your model. So that's what you can do in federated learning. That if your model is basically suffer from the adversarial attack, your model will basically also suffer from the backdoor attacks. So that's the first result we proved in theory. And second result is that so detecting backdoor can be quite hard, computationally hard. So there's basically no cheap way you can use to basically detecting if the model is containing a backdoor or not. Also, especially if your model is basically containing an edge case backdoor, so there's just no way you can basically just use the first order method to basically detect if the backdoor exists in that model or not. So basically the conclusion here is that so backdoor are basically inevitable in federated learning especially, and really hard to deal with. So empirically, what we found is that so if we just use the Southwest airline example, as I described previously, and try to use that as your backdoor pattern to insert into the global model. So what we observed in our experiment is that for the mean task accuracy, so basically imagine that we are just training the CFR10 image classification classifier like jointly in the federated learning. So mean task accuracy here is basically how well your global model predict on the CFR10 test data set. So so basically the mean task accuracy looks great during the whole training procedure. So in that sense, like if you want to use the global holdout test data set to check if there exists a backdoor, there will be no chance that test will be successful. And also, if we make the like attack full edge case, basically only the attacker can see the Southwest airline example, the attack will be quite effective. But if we make the like a edge case example almost edge case, basically meaning the attacker has most of the edge case examples, say here Southwest airline examples, and other honest user can seldomly see the edge case example with clean label. So attack can still be effective. But if we just make the edge case pattern quite common, so everyone can basically frequently observe the Southwest airline example, then the attack won't be successful. That aligns with the Google's observation that attack can be successful in some of the round, but will not persist. So edge case example is quite important here to make the backdoor persist long. So remember that in the Google paper, it also claimed that the simple defense method can just work to defend against the backdoor. We basically test our edge case backdoor in a whole bunch of popular defenses methods we can find in the literature. Here is the multi-chrome and the chrome and the RFA and norm clipping. So it seems that so most of the attacks by just using the black box attack, and also just the attack can be quite effective. And mostly for the white box attack, if we are allowed to use PGD, the attack can be quite effective to basically comparing against the all the state-of-the-art defenses method. So so another basically experiment we want to study here is that so how much attacking effort is needed for the attack. So what we found here is that in the left figure, so we basically fix the pool for the attackers in the participating user population. So basically what we found is that if you just allow 2% of the attacker, 2% of the user to be attacker, so the attack will be quite effective in practice. Or if you just allow the attacker to participate in one of the 10 federated learning rounds, the attack will be effective. So you don't need a lot of attackers or attacking frequently to make the backdoor attack effective in the real federated learning game. And also, there's another interesting effect we observed in our experiment is that, so since mostly of the modern neural network are all parameterized, so if you have more model capacity in your model, it's actually easier for the attacker to insert backdoor attack into your model. So here we basically tried 3 different models with the same model architecture. It's basically VGG9, and we basically control the widening factor of VGG9. So basically observe that for a wider model, it's actually easier to insert the backdoor in the sense that the backdoor is more effective given the certain federated learning rounds. So larger model capacity actually leads to better attacking effectiveness. There's another even more interesting effect I want to share with you is that, so when we actually try hard to defend against the backdoor attack, you may actually raise fairness issues. So here is a quite interesting experiment we basically conduct in our paper, is that we basically have like 200 participating users in total. And we basically just let the client 1, it's actually even not included in the 200 users as an attacker. So this basically holds the edge case example with poison label. So say Southwest airline examples with the poison label as truck. So we also have another subgroup of the participating user, say client 0 to 9, that also holds the edge case example, say Southwest airline, but with the correct label. And so we basically run the federated learning game with some certain type of defenses on the global model, say chrome and multi-chrome. So what it does is basically it just filter out the a group of like users updates. And here we run the federated learning for multiple rounds, and we count like how many times that each user's updates is accepted by the data center. So here, if we run Chrome, so interestingly, we observe that both of the clients and both of the attacker and other honest clients with Southwest airline example do not accepted by the global model. And in the multi-chrome, actually, it will accept several of them. That's only because the multi-chrome has more budget to accept like model updates. So sometimes if there's a lot of like workers want to upload their models with Southwest example, multi-chrome has to accept several of them. So here, the conclusion here is that, so if you try to use the certain type of defenses on the global model, it will basically tend to reject the workers that are trying to introduce a new information to the global model. So basically, if there are users from the tail distribution, but they actually want to contribute to the game for some previously unseen information, so the defense will basically reject them. So that will basically directly raise the fairness concerns. So so our work is actually not only like published in our GitHub, we also integrate that into several federated learning like framework. So together with a group of researchers from industry and academia, we actually developed this FedML framework. So we basically inserted our backdoor edge case backdoor into this framework. Like just feel free to try to go to the fedml.ai. And our white paper actually won the best paper award at Spicy FL workshop and your team. So yeah, definitely just if you're interested, just go there to try it out. So the conclusion here is that, so we arrived at the conclusion that federated learning is vulnerable to backdoor attack. And also, if you really want robustness, so robustness does not come for free. So you may pay extra price in either privacy or fairness. So future work can be, so how to make the trade-off between fairness, robustness, and privacy. There's one recent work, so kind of one recent also work by TND and Virginia is actually from basically accepted by ICML this year. They're trying to make the balance the fairness and the robustness in federated learning. So I encourage you to check that. And also, so one thing we do not consider in our framework is that how can different attackers, if in the same distribution, if there's more than one attacker participating in the federated learning game, how can they collude to make this attacker to make the attack even stronger? And also to generate the edge case example, you basically so currently the current version is sort of like chosen by manual like selection. So how can we handle propose the methodological approach to basically generate edge case examples? So those are the quite interesting open problems to me. And yeah, by that I will basically stop here and start to take some more questions if there are any.
Thank you, Hongyi, for a great talk. So please, if you have any questions, just raise your hand. Or okay, so we have one question. I'll try to unmute there. So please go ahead.
Yes, hello. Thanks a lot for the nice talk. I was wondering if you could elaborate a little bit on this third point of future work of how to determine edge or how to generate edge case examples, because you also had a slide on the spectrum of the data distribution, right? And that United Airlines is maybe more common than Southwest. Although I'm not sure how that's compared to CFAR10, if there are even any United Airline airplanes in the CFAR10 dataset. But yeah, I don't know, maybe if you have any thoughts on what can you term as the distribution, or how can we find these kind of groups of edge case examples?
Yeah, that's definitely a fundamental question. That's a great question. It's also a quite fundamental questions we need to address in the beyond the current version. So here is definitely there's no Southwest or United like airline examples in the CFAR10 dataset, and so in our experiment we actually try to download those kind of like images, and we sort of like resize those images and downscale them to the CFAR10 resolution, and make those as some extra data points in our experiment. So yeah, so like by some simulation, you can definitely make those images as like either like an edge case example or just a common example. So that's one thing I want to answer. So second is that so there might be some systematic way to handle to check if there's one. So for attacker, I basically can have several images, and so basically to check that, I can just basically sort of like learn like generative model on the common data set, and then I basically can check if and I basically have a subgroup of the edge case users, edge case data points. And then basically I can leverage the generative model to basically see if my candidate edge case subdata set, sort of like how that distribution align with like a common distribution, say the CFAR10 data set. Yeah, there might be some potential approach to achieve that, but I don't think currently there's a clear answer to that question.
Right, thanks a lot.
Yeah, thanks for the great question.
Another question from Konstantin by Madison.
Thank you very much for your talk. It was very interesting. I have opened FedML paper, and can you describe what is the main focus of FedML framework? Because by figure 1 from the paper, it seems that it has a lot of targets. Like it contains NAS, it contains integration into NVIDIA platforms, Raspberry Pi platforms. And also it has benchmarks. So are you going, so what, do you have specific goal of this platform, or is it, I'm asking because even some aspects of FedML, of federated learning, like secure, like Andrew Trust create a separate framework to integrate into PyTorch. And it's already a big bunch of work to support technology from cryptography community. So what is your main goal in FedML?
Yeah, great question, great question. So yeah, thanks a lot for raising that point. So so I think the main, okay, so the one sentence contribution here is that we want to like try to introduce the infrastructure to a research community. So so we all kind of like discussing the federated learning like you know, like it's a quite active area now in academia. But if we look at the experiments in the so most of the paper, which is sort of like trying to simulate the federated learning environment. So here, like even if we have multiple GPUs, like what will be the the basically easiest way to leverage all the computing resources to simulate the federated environment here. Say if we are given 100 GPUs, how can we make best use of them to simulate our federated learning environment? So that's actually one of the key key problem we want to solve by introducing this framework. Basically, try to provide infrastructure to the federated learning researchers in academia. So you can basically just directly like plug your method in, and just the framework will help you to leverage to make a full use of your hardware. So that's one thing. The second thing is that we want to try to find the easy way to benchmark the method and compare against each of the different methods in federated learning. So we basically try the best to support all different ways to simulate the heterogeneity in the data environment, and basically tried our best to integrate all the like basically popular or existing method into the framework, such that if you can just you can basically run those in the same aligned environment to make the data consistency and the kind of like the configuration consistency, so you can make it easier to benchmark result and make comparisons. Yeah, so basically this framework gives people a way to accelerate their research, when you actually try to conduct federated learning research. And for the security, we definitely also integrated into the secure aggregation into this framework. So basically, I think currently everything's there, and yeah, it just gives the researchers a better environment to conduct their experiment and make fair comparisons.
Okay, thank you. And you have a label of Stanford University, and there are a lot of different interesting professors at Stanford, but to best of my knowledge, there are no professors at Stanford who is working on federated learning. Maybe I'm wrong.
Yeah, it's right. That is one collaborator who was a postdoc at Stanford. So he's currently assistant professor at Hong Kong, like HKUST. So yeah, so I put that is just one of the collaborator was at Stanford. So yeah, but I agree. I don't think there's I can't think of any specific name that Stanford is currently focusing on federated learning. Yeah, I think you're right.
Okay, thank you.
So is there any other question? So in the meantime, I would have maybe two quick questions. So first one, Hongyi, so for the FedMA, can you actually guarantee, for instance, from theory point of view, that like that running FedMA is always better than just doing naive aggregation?
Oh yeah, so I think yeah, so I think it's hard to say we can always guarantee like you're running faster than aggregation. So if we just consider the aggregation step, it's actually slower compared to coordinate device averaging. That's for sure. So if you have a huge layer, it's like quite a wide layer, like for each of the local model, then the runtime, the complexity will actually becomes like a cubic with respect to the width of the network, which is actually linear for averaging. So in that step, you cannot guarantee that. But if you are allowed, so if your scale becomes larger, and if you are allowed to train the fewer federated learning rounds, then there is a chance that you can actually run faster, well, compared to federated averaging.
So maybe so can you, for instance, at least guarantee that with respect to communicated bits, you will be you would improve because each round costs the same amount of communicated bits. So with respect to that, can you actually guarantee that you should be better? On the, for instance, on theoretical level.
Yeah, we actually don't have any. So currently the work is a pure empirical. Yeah, but we definitely want to see some theoretical guarantee if there are way to conduct the theoretical analysis on top of that. Yeah, so currently the work is pure empirical, but yeah, I'm definitely more than happy to see if there are any theoretical result on top of that can be conducted.
So, and one extra question, with respect to both of the works that you presented. So what do you think about, is FedMA more prone to being a backdoor to than standard federated averaging? Because it's it tries to preserve the output of each client. So do you think that actually you would see more backdoors there than standard federated averaging?
Yeah, it's a great question. So yeah, I actually think that will be, yeah. So we actually have an experimental result in the paper of FedMA. So basically, it actually protects the tail user. So it actually preserves the structure that's trying to extract it by the tail user. So it's easy to imagine. I mean, if I'm from a distribution that's quite far away from the central distribution, my feature extractor might look quite different from all other users. So since we know most of the images from the ImageNet dataset are actually from American or European regions. If I'm an African user, so my feature extractor would definitely look different from the normal users. In that sense, FedMA actually preserves the feature extractor from those tail users. Now, I would definitely imagine that if the tail users are attacker, then it can be the case FedMA is more vulnerable to backdoor attack. Yeah, that's a valid point.
Yeah. Thank you. So, any other questions? So I guess we have 2 more minutes. So it seems there is no other question. Yes, thank you, Hongyi, for your great talk. It was a pleasure to host you, and we will continue next week. And we will have a talk by Stefanos Laskaridis from Samsung AI Cambridge. Okay, so thank you everybody for attending. Thanks again, Hongyi, for a great talk.
Thanks a lot, everyone, for attending. Yeah, thanks a lot for having me.
And see you all hopefully next week. Bye-bye.
See you. Bye.